Welcome. Today, we're going to break down one of the coolest real-world applications of integrals, calculating hydrostatic force. Seriously, if you've ever wondered how dams hold back all that water, or why submarine windows are so thick, you are in exactly the right place.
All right, here's the game plan. We're going to start with a basic idea of what hydrostatic force even is. Then I'll give you the master formula that unlocks everything. We'll walk through a nice, simple example, then level up to some trickier problems, and finally, we'll wrap up with the absolute must-know takeaways.
So first things first, before we even think about writing an integral, let's just build up an intuition for what it is we're trying to figure out. Think about it, right? The answer comes down to a really simple principle in physics. The deeper you go in any fluid, water, whatever, the greater the pressure gets. This means that a single submarine window actually has more force pushing on its bottom edge than it does on its top edge. Wild, huh? And here's the cool part. We can actually put a number on that pressure. The formula you see here, P equals rho GD, tells us exactly how. It's just the fluid's density times gravity times the depth. Now for water, that density times gravity part works out to be about 9,800. You're going to want to just lock that number away in your brain. It's super useful. But, and this is a really important distinction, pressure is not force. They're related, but they're not the same thing. To get the actual force that's pushing on a surface, you have to multiply the pressure by the area it's acting on. Now, if pressure was the same everywhere on that surface, we'd be done. But, as we just saw, it's not. And that changing pressure, well, that creates a problem for us. How in the world do you calculate a total force when the pressure is different at every single point down a vertical surface? This, my friends, is where calculus comes swooping in to save the day. And this is the master formula. It perfectly captures the big idea. What we're doing is we're imagining that we slice that submerged object into a bunch of infinitely thin, horizontal strips. Think of it like a stock of paper. On each one of those tiny strips, the pressure is basically constant. So we find the force on that one little strip, and then the integral does the magic of adding up the forces on all of them. So to solve pretty much any of these problems, you just have to follow these 4 steps. 1, set up your coordinate system, usually with y equals 0 at the surface. 2, figure out an expression for the depth. 3, figure out an expression for the width. And 4, plug all that stuff into the integral and solve it. That's the blueprint. Okay, let's put this formula to the test. We'll start with a nice, simple shape to really see how this 4-step process works in practice. All right, here's our setup. We've got a basic rectangular plate. It's 2 meters wide, 3 meters tall, and its top edge is sitting right at the surface of the water. Our mission is to find the total force pushing on this thing. Okay, following our steps. We'll set y equals 0 at the surface and have y increase as we go down. So at any point on the plate, the depth is just y. Easy enough. And since it's a rectangle, the width doesn't change. It's a constant 2 meters all the way down. See, the setup for a rectangle is pretty straightforward. Now we just plug all of those pieces into our master formula. We've got 9,800 for the rho g part, we have y for our depth, we've got 2 for our width, and since the plate starts at the surface, y equals 0, and goes down 3 meters, our limits of integration are from 0 to 3. And when you run the numbers, pull out the constants, and evaluate that pretty simple integral, you get your final answer, a total force of 88,200 newtons. So what does that number even mean? 88,200 newtons? Well, to put that into perspective, that's roughly the same as the weight of 9 small cars, all pushing against that plate at the same time. That is an incredible amount of force from just a few meters of water. Okay, so we've got the basics down with a nice, easy rectangle. But now let's level up and tackle some problems where things get a little more interesting. This is where you really see the power of calculus. So for our next challenge, we've got a shape where the width is no longer constant. We have this upside-down triangular gate, and we need to find the total force on it. Okay, so here's the big hurdle. We can't just plug in a single number for the width anymore, right? It's wide at the top, and it narrows to a point at the bottom. So we need to express this changing width as a function of our depth variable, y. And the way to do that is with similar triangles. You set up a ratio comparing the big triangle to a smaller one at some arbitrary depth y, and that lets you derive the function for the width. All right, so weird shapes are one challenge. Here's another common trap. What happens when the object isn't right at the surface? A huge, huge mistake people make is just automatically integrating from 0 every time. You absolutely have to adjust your limits of integration to match where the object actually is. Take this situation, for example. We've got a small 1 by 1 meter square plate, but its top edge is already 10 meters deep. Now, even though this plate is way smaller than our first rectangle, you'll see that its depth is going to have a massive impact on the calculation. The setup follows the exact same logic. The width is a constant 1, and the depth is our variable y. But here's the crucial part, the limits. This plate doesn't exist from 0 to 1. It exists from a depth of 10 meters down to 11 meters. So we absolutely must integrate from 10 to 11. And check out the result, 102,900 newtons. That is more force than what was acting on that much, much larger rectangle in our first example. It's a perfect demonstration of just how critical depth is in these calculations.
Phew, okay, that was a lot to take in. Let's do a quick recap of the most important things to remember so you can walk away from this with the core concepts really locked in place. So, remember these key ideas. At its heart, hydrostatic force is just the integral of pressure over an area. That pressure always increases in a straight line with depth. If your shape is anything other than a rectangle, you're going to need to find a function for the width. And always, always, always pay attention to your limits of integration. They tell the story of where your object is. The whole idea here is slicing a hard problem into easy pieces and then letting the integral do the heavy lifting of adding them all up. So the next time you see a dam or even just a deep swimming pool, think about the incredible invisible forces at play and the beautiful bit of calculus that lets us understand them. It really makes you wonder, what other hidden forces and quantities can integration help us uncover all around us? Thanks for diving into this with me.